Okay, so first of all, I would like to welcome everyone and thanks for choosing to attend this webinar about performing logistic regression using SPSS software. I'm Nasser Hasan. I'm a PhD student at the Research Measurement and Evaluation program at the University of Miami. So today I'm going to briefly talk about logistic, the idea, the concept of logistic regression and when to use it. And then I'm going to walk you through performing the analysis using SPSS and how to interpret the results. So first, let's talk about the idea of logistic regression. So logistic regression is used to predict a categorical dependent variable from a set of predictor variables. And usually the dependent variable is dichotomous or let's say binomial. So for our logistic regression, usually the predicted dependent variable is a function of the probability that a particular subject will be in one of the categories of or the levels of the dependent variable. So an example for when to use logistic regression will be if the researcher wants to understand whether exam performance that is measured by either passed or failed, so you can see it's a dichotomous variable, can be predicted based on revision time, test anxiety, and lecture attendance. Or also the second example, if you can see, the researcher wants to understand whether drug use that is measured by either yes, the participant is using drugs, or no, can be predicted based on prior criminal convictions and drug use amongst friends, income, age, and gender. So basically the idea is to predict a dichotomous dependent variable from a set of predicted predictors or predicted variable, or let's say, in other words, independent variables. Usually when we deal with logistic regression, we assume that there are no assumptions, but there are 4 important assumptions that we should be aware of it before doing or performing any analysis. So the first assumption is, So the first assumption is your dependent variable should be measured on a dichotomous scale, or binary scale, or binomial scale. The second assumption is you have one or more independent variables or predictors, which can be either continuous or categorical. So they can be either, they can be a mix of the two types. 3, you should have independence of observations, and the dependent variable should have mutually exclusive and exhaustive categories. The fourth assumption is the most important one. So this is the one that we assess through SPSS, and usually people do not report it in the real life, but to do the analysis in an appropriate way, you have to check this assumption. So there needs to be a linear relationship between any continuous independent variables and the logit transformation of the dependent variable. And this could be done by the Box-Tidwell test. So the Box-Tidwell test is basically we include in the model the interactions between the continuous predictors and their logs. If the interaction term is statistically significant, that means the original continuous independent variable is not linearly related to the logit of the dependent variable, and therefore the assumption is violated. And this assumption is, this test actually is a function of a sample size. So sometimes if you have a large sample size, you will get significant interaction results. So don't worry about the significant interaction if the sample sizes are too large. So any questions so far before moving on? You can type the questions in the chat if you want. Otherwise, I will continue. How large a sample size? I will say larger than maybe 50 or 100 maybe. So it depends on the field, I would say. But just keep it in mind that sometimes if you have a large sample size, you may see a significant interaction effect. You're welcome. Okay, so let's do the analysis then. So I'm going to use a data set that you can find on this link. So please, I will give you about 5 minutes to download this data set and open it in SPSS, please. Let me just copy the link and paste it in the chat if it's possible. Sure. So here's the link. And if you have the chance to download it and open it in SPSS, could you please just use the thumbs up sign or clap sign, anything that will let me know that you guys did it? I can see a few people said that they got it and opened as well. Let's just give a couple of minutes. Okay, so it seems like everyone got the data set, and I guess we are ready to go. So let's just give a quick look on the data set. Just make sure that you have 6 variables in your data set. Our dependent variable in this study will be the heart disease. So basically, we want to look at whether age, weight, gender, and oxygen max levels will predict if someone has a heart disease or not. So this is why we are going to use a logistic regression analysis to answer this type of question, because our dependent variable heart disease is a dichotomous variable, which is whether the participant has a heart disease or not. So all others are independent variable except the case identifier variable, the case number. Usually this is very helpful and used when we want to check for any outliers or anything that could mess our results. So this is why we usually include the case number, but it's not included in our model to predict the heart disease. So the variables in our model will be will be serving as an independent variables are age, which is the participant age in years, and it's measured in a continuous scale. The second one is weight, which is the participant's weight, or technically their mass, and it's actually continuous as well. The other one is gender, and it has two categories, male and female, and it's categorical. And the last independent variable is the VO2 max, which is the maximal aerobic capacity, and it's continuous. So just make sure that each of them has the appropriate measure, because later on you should you will see that you have to specify each measure correctly to do the analysis, to do the logistic regression analysis. Okay, so before moving and doing any analysis, we want to make sure that the fourth assumption, the one about the linear relationship between any continuous independent variables and the logit transformation of the dependent variable using Box-Tidwell test is assumed. So in order to do this, first we should compute a new variable that is the logs, the natural logs of the continuous variable, and then we add the interaction term between them, between the continuous independent variable and its log to the model, and to check whether the interaction is significant or not. And remember that we want it not to be significant. So how can we do that? First, we should compute a new variable that is the log of any continuous independent variable in our analysis. So we want to do it 3 times, one for age, one for weight, and the last one for the VO2 max. So you want to click on transform, then compute variable, and this window will pop up. Minimize it. So is everyone following? If you could type yes or no in the chat. Good. By the way, can anyone look at the webinar chat if I share my screen, or it's not there? Are you able to see the chat from my screen? Okay, good. So someone is asking why we should perform the log and not just complete the regression. So in order to proceed with the analysis, you should check the assumption. So the fourth assumption should be assessed through this way. So you have to compute the log for each continuous independent variable. And then at the first step, you should include the interaction between this log value with the original continuous independent variable value as an interaction term in the model. And you want this interaction to be not significant in order to say that the assumption was met. I hope this answered your questions. Okay, so how can we do this? First, let's name a new variable and the target variable, and I will call it ln age. And the formula for calculating or computing the log of age is using ln, open a parentheses, and just put age in it between the parentheses. So is everyone following, or you want me to repeat this step? Is everyone following? Yes, no? Good. Okay, so then you want to click on OK. So let's wait until the analysis is done. Okay, so it was computed, and you can see that there is a new column, a new variable called lnh. So we want to do this also for weight and VO2 max. So go again to transform, compute variable, and we just want to change age to weight, and we want to add weight here, and then OK. And there is an easy way if you are familiar with the syntax stuff, but it's like a whole story. So I will just do the easy way. VO2 max. And you want to do this only for continuous independent variables. So you don't want to do it for gender. So are we good? Should I move forward and see how can we assess the assumption? And just make sure that you got 3 new columns, 3 new variables for each continuous independent variable. In this case, age, weight, and VO2 max. Okay, so right now we are just going to do like a fake logistic regression analysis just to get the results of the interaction term and to assess the to perform actually the box Sidwell test. So you want to click on analyze, then scroll down to regression, then binary logistic. So again, you have to go and click on analyze, then regression, then binary logistic, and this window, this logistic regression window will pop up. So as I said, we will run a fake analysis at the beginning just to check this assumption before going forward and do the real analysis. So let's add our dependent variable in the dependent box and all other independent variables in the covariates box. This is just the first step again. So you should move the dependent variable to the dependent variable box and all other independent variables in the covariates box. Then to assess the assumption, we should add the interaction between each independent variable and its log value as an interaction term in the covariates box. So if you are a Mac user, you should click on age, then hold the command button and choose the ln_age. So in this way, you will highlight both variables. And then if you can see the A times B button here, if you click on it, you will see a new interaction term between age, the original independent, the original continuous independent variable with its log value is added as a covariate. Are you able to get this? And of course, you should do it for the other two continuous independent variables. So let's do it for weight and VO2 max. So again, highlight weight, ln weight, and then add it as an interaction term. Make sure it's there. And VO2 max, ln VO2 max. Are we good? Should I move? Okay, seems everyone is following up. So let's go and do the next step. So in the logistic regression window, you can see that there is a categorical button here. So if you want to click on the categorical button, you can see that you have one categorical predictor or independent variable. So you want to define this and to decide which level is considered as a reference category. So move gender to the categorical covariates first by highlighting it and then moving it to the categorical covariates box. And if we go back to the data set, you can see that gender is either male or female. So I forget which one was 1 and which one was 0 or 2. So let's say I want the first category, the first value to be the reference. So you want to click on first. And by the way, by default, the reference category is always the last one. So I want to modify it and to change it to the first. So click on first and then click on change. So you can see that gender was classified as a categorical covariate and the indicator or the reference is the first group or the first level. And then continue. Then click on options. So in options window, or subcommand, you will see some statistics and plots that are necessary for our analysis. So for this analysis, we don't want any statistics because we will not base our results on it. But however, I will say just go and click the statistics and plots needed for the analysis, just because if you assess the assumption, you will just go back and delete the interaction terms and just rerun the analysis. So you don't have to click on the options again and do all the things again. So the statistics we need for this analysis is classification plots, Hosmer Olympio goodness of fit. You want also to click on case-wise listing of residuals just to identify any outliers. And usually we keep the outliers range within 2 standard deviations. If you want to be more strict, say 1.5, or you want to be really super liberal about it, so you can put a 3, but I will keep it 2. You want also to add the confidence interval for the exponential standardized coefficients, B or beta. And we don't want to display the statistics for each step. We want it only for the last step. This is the number of probabilities of stepwise. Okay, we don't want to play with anything else. That's it. Just hit on continue, and you should be ready to run the analysis. So if you did everything, you don't want also to play with the method. Just keep it as default. Okay, then hit on OK. And let's look at the output. So remember that we are not doing the real analysis. We just want to assess the fourth assumption using the Box-Tidwell test technique. So you want to scroll down until the block 1 and go directly to the variables in the equation table. So it's kind of the last table or at the end. And look at the interaction terms right here. Remember that we don't want the interaction terms to be significant. Otherwise, we violated the assumption. And you should also note that sometimes if you have a large sample size, you will get a significant interaction effect. Okay, so our sample size is 100, I guess. So it's a kind of large sample size. So let's go back to look at the significance of the interaction effects. So you can see that the interaction effect between age and the log of age is significant, meaning that it was violated for age, and the other two was not significant, meaning that they are good. So should we proceed or not, depending on how you look at it and how large your sample size is. I will say I will proceed with this one, but I will report it. I will say that this was violated because we found a significant interaction term. And this could be due to the large sample size that we deal with it. So you may say that, or you may just ignore it and proceed with your analysis. So this is how you look at the fourth assumption by performing a Box-Tidwell technique or test. So is it clear? or you have any questions about it? Okay. So we are only looking at the ln variables in the box. Yeah, we are looking at the interaction terms between the ln age and age. I mean the original continuous independent variable with its log. Yes, this is what we are looking at. You're welcome. Okay, remember that this is not the real analysis. So just to perform the real analysis, we have to delete the interaction term when we want to redo the analysis. So just go back to SPSS, analyze, regression, binary logistic, and you will see everything was saved. And you just want to highlight the interaction terms and return them. So in block 1 of 1, you want to see only your 4 independent variables. And we don't have to mess with the categorical button or options subcomments, because we already did everything and we click on what we need for this analysis. Are we good? Okay. So someone is asking, would we not include the main effects of the ln variables since we are including the interaction terms? So yeah, I didn't include, if you can go back, if I can go back to the slides, let me show you. Yeah, so I was not including the main effects of the ln variables. I was including the main, the original continuous independent variables. So the ln was added as an interaction terms by its original continuous independent variable, by its original value. So I didn't include the main effects of the ln variables. I hope this answered your questions, Patrice. Let's just wait and make sure that I answered the questions. Okay, it seems like everyone is following up. Yep. Okay, so this is what the logistic regression window should look like. Then you want to hit on OK to perform the real analysis. Okay, let me move the output here. So is everyone able to look at my output window? Good. So in the output, you can see that you have 3 parts. So this is the first part, and block 0 is the second part, and the block 1 is the third part. So I will look at each part and I will say the needed information if you want to report your results. in the results section if you are performing such analysis in your study. So this part, the first part, tells you about the cases that were included and excluded from the analysis and the coding of the dependent variables. So if you can look at the first table, you can see that how many cases included in the analysis, and we have 100 here, no missing cases, and no unselected cases. And also we can look at the coding of the dependent variables. So no was coded as 0, and yes was coded as 1. I mean, yes having heart disease, and no not having heart disease. And also, if you remember, we specify gender to be a categorical covariate. So SPSS do not give each level a code automatically. So you should do this step in order to get this table. So this table shows you that gender, the female was giving, remember that we decided to, I think we said that the first group is the reference. So SPSS understands that female will be coded as 0 and male will be coded as 1. So you have to do this step manually because SPSS do not do this step for you automatically. So this is all about how many number of cases included and excluded and etc. So there is nothing that you really want to include in your results section. So let's move to the second part, the block block 0, the beginning block. So this part of the output describes a null model, which is a model with no predictors and just the intercept. And you can see that there are the variables and the equations are just the constant, or we call it sometimes the intercept. So our independent variables were not included in this model, which is a step 0 model. What does actually this tells us? So if you look at the classification table, it tells us that without including any independent variable, this model correctly identify 65% of the cases. So in the second model, we want to look at whether this 65% percentage was improved or not when we added our independent variables. So, I mean, we cannot, this block is kind of not informative, very informative about our original model. So this is the only thing that you want to know about this part of the output. So I will focus more on the third part of the output, which is the block 1, and it's our original model. So the first table, the omnibus tests of model of coefficients, we can see that overall our model significantly and statistically significant, because if we look at the significant column here, we can see it is significant based on your alpha level. So let's say we are using 0.05 alpha level. So this value was very less than 0.05. So indicating that our overall model is statistically significant in predicting the heart disease, whether someone has a heart disease or not. Are we good? So this is just about the first table. We didn't talk about the others yet. Okay, so the second table, which is the model summary table, it's kind of serving as the R-squared doing in the multiple regression model. So if you remember in the linear regression model, the R-squared was served as the variance explained by the model. Here we cannot say this directly, but with caution. So this table contains the Cox and Snell R-square, Nagelkircher, Nagel-Kirk R-square values, which are both methods of calculating the explained variation of the model. So these values are sometimes, these two are sometimes referred to as pseudo-R square values and will have lower values than in multiple linear regression. However, they are interpreted in the same manner, but with more caution, as I said. So we can say that the explained variation in the dependent variable, whether someone has a heart disease or not, based on our model, ranges from 24% or 33%, depending on which method we use. So this is how you will interpret this table in your results section. Are we good? And by the way, the Nagel Kirk is the preferred one. So usually people go with this. Okay, so let's move to the third table, the Hosmer and Olympio test. So the Hosmer-Olympio test, the null hypothesis that the predictions made by the model fit perfectly with observed group memberships. So it's using a chi-square statistics to compare the observed frequencies with those expected under the linear model. And we want the result to be non-significant. So a non-significant chi-square value, as in our example, indicates that the data fit the model very well. So it's not the best, but it's fitting very well. So it's not fitting very weak. This is how we interpret this result. So again, this is, you will find this one in the PDF files. So if you don't worry about it, so you will find everything in the PDF file. So you don't have to write down everything, just to make it easier for you. Okay, so the contingency table for Hosmer and Olympio tests usually is not used in our results section. So we cannot say anything about this table. And it is, it's not very informative. And we want to move to the classification table. So this table has so many information in it. So first information is the accuracy in classification. So if you go back to the part 2, you can see that the overall percentage of correct classification, or the accuracy, was 65 without including any independent variable in it. When we added our independent variables, this was improved to 71. So we can say that with the independent variables added, the model now correctly classifies 71% of the cases overall. And we want to look at the overall percentage row. And this is referred to the term, to the accuracy term. So if someone is asking you about the accuracy of your model, this is where you want to look at the overall percentage. And this is very often used in the medical field. And there are also two other terms, which is the sensitivity and the specificity. So if we want to look at the sensitivity, this is where we want to look. So we can say that 45.7% of the participants who had heart disease were also predicted by the model to have heart disease. So if we want to look at the percentage correct column here in the yes row of the observed. So this is referred to the sensitivity. Regarding specificity, this is the value we want to look at, the percentage correct column in the no row of the observed. So this tells us that 84.6% of the participants who did not have any heart disease were correctly predicted by the model not to have heart disease. Is the three terms clearly understood before moving to the other two terms? Again, we have the accuracy, and then we have the sensitivity, and then we have specificity. Okay, good. So let's move to another two terms, which are the positive predictive value and the negative predictive value. So let me share with you this in order to make it easier for you to look at the table and what I'm talking about. Okay. So if we want to look at the positive predictive value, it is the percentage of correctly predicted cases with the observed characteristic compared to the total number of cases predicted as having the characteristic. So we want to look at, if we want to look at the positive, we will go to the yes column in the predicted, and to see how many cases here, how many cases were identified or classified as having the characteristic, which is 16 divided by the total. So divided by 16 plus 10, and then multiply it by 100 in order to get the percentage. So it is 61, and that is interpreted as of all cases predicted as having heart disease, only 61.5 were correctly predicted. And if you want to look at the no column, and that is the percentage of correctly predicted cases without the characteristic compared to the total number of cases predicted as not having the characteristic. So in our case, not having is 55, and we want to divide 55 by the sum of 55 and 9, and then multiply it by 100. We will get 74.3%, and that is interpreted as of all cases predicted as not having heart disease, only 74.3% were correctly predicted as not having the characteristic. So this is how we talk about this classification table, and you can see how much information we can gain from this table. So is it clear before moving to the later table, to the next one? Good. Good. So it seems like everyone is following. Okay, so let's move to the variables in the equation table. What does this tell us? So first of all, you want to look at the wald statistic column, which is used to determine the statistical significance for each of the independent variables in our model. So this test follows chi-square distribution with the degrees of freedom of 1. So you will always see 1 as the degrees of freedom. And the significant column is basically tell us whether this independent variable is a significant independent variable in predicting the dependent variable or not. So if we look at age, we can see that age was significant predictor. Weight was not a significant predictor, and gender was a significant predictor, and VO2 max was also a significant predictor, assuming that we are using an alpha level of 0.05. So this is about wald and degrees of freedom and the level of significance. And I have to mention that the beta, or the coefficient is telling you whether it's predicting the dependent variable in a positive way, or a negative way. So we can see that all independent variables except VO2 max is kind of going in an increasing way with the dependent variable. However, VO2 max is going in a negative way. So if VO2 max value increases, the dependent variable will be less likely to happen. So we also can use this exponential beta value to kind of how can I say this in an appropriate way? So, for example, let's say that we said that female is the reference group. So we can see that the value here is 7.03. The way of interpreting this result is to say that the odds of having heart disease is 7.03 times greater for males as opposite to females. Again, so if you want to interpret this result, you can see that with keeping all other independent variables constant, the odds of having heart disease is 7.03 times greater for males than our reference group, which is the females. So is it clear? Before moving to the APSI write-up? Okay, so how would we write the results in an APS style format? So usually you want to say which type of analysis you performed. So in this case, we will say that a logistic regression was performed to ascertain the effects of age, weight, gender, and VO2 max on the likelihood that participants have heart disease or not, or whether participants have heart disease or not. So this was the main goal of the analysis and how we assessed it. Then move to the overall model. So we saw that the logistic regression model was statistically significant. Let's go back to the table and show you which table exactly is it. So this was the table, the first table. So we can see that the overall model is significant with a chi-square value of 27.40 and degrees of freedom of 4. Then we want to move and talk about how the variation explained by the model. So if you just go back to the model summary, whether you decided to go with Cox and Snell or Nagel Kirk method, you can see that this value is kind of interpreted as a variance explained by the model in heart disease. So I will say that usually people go with Nagel Kirk R square. So I can say that the model explained 33% of the variance in our dependent variable, which is the heart disease, whether participants had heart disease or not, and correctly classified how many cases. So if you go back to this table, you can see that overall the accuracy or the number of the percentage of correctly classified cases was 71. This was by the overall model. And you want to add this. Then move to each independent variable and talk about it using variables in the equation table. So as I said, that males were 7.02 times more likely to exhibit heart disease than females. And we got this from this value, the exponential of beta for gender. And remember why we say males before females, because it was the female was the reference group. So we compare males to females. Okay. Also, we can say that increasing age was associated with an increased likelihood of exhibiting heart disease. And also we get this from here. So we can see that age was kind of positively or related in a positive way with the predicted, with the dependent variable, and it was also significant. So we can say if the age increases, the likelihood of having a heart disease will increase as well. And this applied for weight and not for VO2 max because it was negatively related. So we can say that increasing age, again, was associated with an increased likelihood of exhibiting heart disease. And we can say that it was a significant and giving the Wald statistics with its degrees of freedom, which usually or always will be 1. However, increasing VO2 max was associated with a reduction in the likelihood of exhibiting heart disease, because we can clearly see that the relationship was negative here. We didn't talk about weight because it was not significant, but you may want to add it in your write-up and say that weight was not significantly associated with the likelihood of an increase or reduction of exhibiting heart disease. So this is how you perform logistic regression using SPSS. Do you guys have any questions? And remember that always you can ask us any questions regarding your concerns, or if you want to further understand the concepts through our website, and you may find our emails in our website. Thank you so much for listening and choosing to attend this webinar. I hope I covered everything. If you guys have, please, 1 minute or a couple of minutes to fill this survey, and we will really appreciate this, because it will definitely help us to improve our webinars in future. So again, the webinar slides will be posted on our website, which is this one. Let me just share the link with you. So this is our website. If you scroll down, you will see the slides, and I will also share the recorded webinar through YouTube in order to follow up if you miss anything. And thank you so much.